Welcome to our video lecture on reduction-oxidation reactions. Our essential understanding for today is that redox reactions, and redox is just short for reduction, oxidation, reduction-oxidation reactions play a key role in many chemical and biochemical processes. We're going to talk a lot about defining reduction-oxidation today. We'll talk more about some of those processes later. So our objectives are to define oxidation and reduction, define and identify oxidizing agents and reducing agents. We're going to practice assigning oxidation states, and then we are going to write some redox half reactions. So here is a little bit of a picture to noodle on, especially for my bio peeps. So we've got some stroma here. Hopefully that is some vocabulary that triggers some thoughts. I've got lumen. I have water molecules that are being split into oxygen gas and some hydrogen ions, also known as protons. Hopefully we are thinking about the fact that this must be photosystem 2, part of chlorophyll and chloroplasts that carry out photosynthesis. So many reduction-oxidation reactions happening here. When we talk about in chloroplasts and in mitochondria, that electron transport chain, oh my goodness, all about reduction and oxidation. So when we say that there are some biochemical processes that redox is important for, oh, that's very true. So let's define oxidation and reduction. So oxidation is when a substance loses electrons. Reduction is when a substance gains electrons or protons. So sometimes, especially in chemistry, biochemistry, we talk a lot about moving electrons and also moving protons. So losing electrons or protons is oxidation, gaining electrons or protons is reduction. Looking at this reaction here, we are going to consider this reaction calcium and hydrogen ions interacting. This neutral calcium, so this calcium is starting neutral, it has a zero charge, it's going to lose 2 electrons, and that's how it becomes calcium with that +2 charge. It lost 2 electrons. If it lost electrons, it was oxidized. Oxidation is losing electrons. If I look at hydrogen now, this hydrogen ion with a +1 charge is going to gain the electrons that calcium gave away, and it becomes hydrogen with a neutral charge. So those 2 electrons that were lost by calcium are gained by those hydrogen ions to form that neutral hydrogen gas. Because hydrogen gained electrons, it was reduced. And here we can see that the charge goes from a +1 down to a 0. And so this is how that charge went down. The charge was reduced. An easy way to remember that oxidation is losing electrons and reduction is gaining electrons is with the amazing mnemonic device, Leo says grr. Lose electrons is oxidation, gain electrons is reduction. A different mnemonic device that you might like better is oil rig. Oxidation is losing, and it's kind of nice because we don't have electrons in here, so we can think about losing electrons or protons, and then reduction is gaining electrons or protons. And this little picture is just showing us super easy that I have this thing, it has an electron, it loses it because it's losing electrons, it's oxidized because this guy got it, it was reduced. All right, so let's practice a little bit with another equation. So what if I react calcium with air? We're basically going to oxidize or rust some calcium. So calcium is starting with a 0 charge because it's neutral. This oxygen is also neutral, it has a 0 charge. Once we make this calcium oxide, oxygen has a -2 oxidation state. Calcium has a +2 oxidation state. Calcium went from 0 to +2. The reason is because it lost 2 electrons. If you lose electrons, you are oxidized. Which species, and I know that's usually a biology word, but we can use it in chemistry as well. Which species was oxidized? Calcium. Calcium was oxidized. Which species was reduced? Well, oxygen went from a 0 down to a -2. That charge went down from 0 down to -2, and it did it because it gained 2 electrons. We went from 0 down to -2, which species was reduced? Oxygen was reduced. All right, so now we're going to add some vocabulary that's going to make things super confusing. Yay! So in all of these redox reactions, one thing is going to be reduced at the same time that something else is oxidized. Those two always go together because I can't lose those electrons and have them go nowhere, and I can't gain electrons if nobody else lost some for me to gain. So oxidation and reduction will always go together. The oxidizing agent is the thing that causes something else to be oxidized. The oxidizing agent is going to make something else lose electrons, and it's going to make something else lose electrons by gaining them, which means that our oxidizing agent is reduced, because to make someone else lose electrons, you have to gain them. But wait, there's more. The reducing agent is the thing that causes something else to be reduced. It's going to cause something else to be reduced by giving electrons away so that other thing can gain them. How you make something else gain electrons is by losing them. So the reducing agent is the thing that loses electrons so that somebody else can gain them, which means the reducing agent is always the thing that is oxidized. The reducing agent makes something else be reduced by it itself being oxidized. Good. So let's practice that a little bit. Let's say that I'm going to make some hydrogen gas by combining metal with an acid. So I'm going to take some magnesium metal and some hydrochloric acid, and we're going to make this hydrogen gas. So our magnesium is going to start with an oxidation state or a charge of 0. It is neutral magnesium. In hydrochloric acid, my hydrogen is going to have a +1 charge and chlorine will have a -1 charge. Over here in the products, magnesium chloride, the magnesium is a +2 charge and chlorine is still a -1. Hydrogen gas by itself is neutral. It's going to have a 0 charge. So to figure out reducing agents and oxidizing agents, the easiest thing to do first is to figure out who is oxidized and who is reduced. So I'm looking at magnesium, who goes from a 0 to a +2. What happened to magnesium to make its charge go up? It got more positive. Well, it had to get more positive by losing electrons. And Leo says Gert. So magnesium was oxidized because it lost electrons. Magnesium was oxidized. That means that it made something else get those electrons. And so magnesium is our reducing agent. Magnesium was oxidized, which means that it made something else be reduced. Let's figure out what that something else is. So I'm looking at, now I'm going to look at hydrogen's charge. Hydrogen goes from a +1 to a 0. We go from a +1 down to a 0. If our charge is going down, we had to have gained some extra electrons to get more negative. If we gain electrons, that is reduction. So hydrogen was reduced from a +1 down to a 0. Because hydrogen was reduced, it took electrons away from magnesium. It made magnesium be oxidized, which means that hydrogen is the oxidizing agent, especially that hydrogen +1 charge, because it's actually the thing that took the electrons. Good. What about chlorine? What is chlorine that had that -1 charge and stayed a -1 charge? We're going to call that guy a spectator ion, because it started at a -1 and it stayed at a -1. It kind of just watched. It was a spectator while all those electrons were being transferred around to everybody else. So one of the most difficult things about redox reactions is being able to assign the oxidation states. Sometimes we call those the charges. And so on these next couple of slides, we're just going to practice assigning all the charges. Free elements, elements that are just by themselves, are always going to be neutrally charged. They will always be a 0. So this oxygen gas, it's just oxygen, it is going to be a 0 charge, it's neutral. Groups 1 and 2 are alkali metals, and our alkaline earth metals will be a +1 and a +2. So this sodium here is a +1, this magnesium here is a +2. Aluminum will always be +3. Hydrogen is a +1 if it's bonded to a non-metal, but it's a -1 if it's bonded to a metal. So I have hydrogen here with chlorine. Chlorine is a non-metal, and so our hydrogen will be +1 here. Chlorine will be -1 here. But sodium hydride, now I have hydrogen with a sodium. Hydrogen is going to be a -1, and that sodium will be a +1. Most of the time, not all the time, but most of the time, the species more to the right is more likely, to be negative, and the species more to the left is more likely to be positive. So hydrogen on the left is more likely positive, hydrogen on the right is more likely negative. Most of the time, there are definitely exceptions to that. Oxygen. Oxygen is -2 unless it's in a peroxide like this guy, in which case oxygen is a -1, hydrogen is a +1. And this makes sense because if I try to balance my charges, +1 times 2 is a +2, -1 times 2 is a -2, and that balances out. And you might be thinking, but wait, that's not an ionic compound. Why am I balancing the charges? You're right, it's not ionic, and yet we're balancing the charges because that's what we do in redox. Everybody gets a charge, even though it might be a pretend or partial charge. All right, so let's do some more. Fluorine is always, always, always going to be -1. Fluorine will never be positive. And so in this guy, are you ready for this? Fluorine is going to be a -1, which means that oxygen is, we just said oxygen is a -2 or a -1. Unless it's with fluorine, in which case, oh my goodness, oxygen's a +2, crazy sauce. All the other halogens will be a -1 in binary compounds, so H plus Cl, that chlorine will be a -1, hydrogen's a +1. But if I add halogens to oxygen, with the exception of fluorine, fluorine is always -1, other halogens, not fluorine, will be positive if I put them with oxygen. What madness! So I'm looking at this guy, HClO4. I'm going to start with my oxygen. I like to always start with the guy most to the right. The guy most to the right in this formula is oxygen. There are 4 of them. Each oxygen is going to be a -2. -2 times 4 means that oxygen's total charge is -8. I'm going to flip over to the far left now. Hydrogen is a +1. There's only 1 of them, so that means that hydrogen's total charge is a +1. Right now I have a +1 and a -8. Are you ready for this madness? Chlorine, in order to balance this molecule, is going to have to be a +7. And you're thinking, chlorine is never going to give away 7 electrons. You're right. But in redox reactions, we go ahead and pretend like they do. But in reality, it's just oxygen's a little bit more electronegative. And so partial charges, that chlorine might be a little bit more positive than the oxygen, but not really +7. But we just call it that so that we can do the math. Good? Good. All right. One more. Iron 3 oxide. Remember that our transition metals, our oxidation state will always be given by that Roman numeral. So this iron will have a charge of +3 because the Roman numeral says so. So let's practice some oxidation states and names. I highly recommend that you pause the video, do these on your own, and then restart the video and check your work. Good? All right, let's do this. So oxygen here, I have oxygen that has a -2 charge. I have 2 oxygens that each have a -2 charge. -2 times 2 is a total of -4, which means that my manganese on the other side is going to have a +4 charge. Oxidation state of manganese is +4. Oxidation state of oxygen, -2. To name this guy, manganese, I'm going to use its oxidation state, Roman numeral 4, in the name, manganese 4 oxide. This one, this is hydroxide. Hydroxide altogether has a charge of -1, but we're going to give charges to each one of those guys. So hydrogen, I know usually the guy furthest to the right is negative, but in this case, hydrogen is +1 and oxygen is -2. -2 plus 1 leaves us with a -1. So the total hydroxide is a -1. I have 2 of them. So this altogether is a -2, which means this copper has to be a +2. The oxidation state of copper is +2. The oxidation state of oxygen is -2. And the oxidation state of hydrogen is +1. And I'm going to call this guy copper 2 hydroxide because the charge of this copper is +2. This is also copper hydroxide, but now I have a +1 on the hydrogen and a -2 on the oxygen. Right now my total is a -1. -2 + 1 is -1, which means that this copper has to be a +1. The oxidation state of copper is +1. The oxidation state of oxygen is -2. The oxidation state of hydrogen is +1. I'm going to call this guy copper 1 hydroxide. Good. All right, let's do this one. I've got some cobalt and some fluorine. Fluorine is going to have a charge of -1. Oxidation state of fluorine is -1. I have 3 of them. -1 times 3 is -3, which means that that cobalt has to have a charge of +3 to balance out the -3 coming from those 3 fluorides. And so cobalt's oxidation state is 3, which means I'm going to call this guy cobalt 3 fluoride. Good. All right, one more. Oh my goodness, this one's messy. I have some oxygen. It's going to have a charge of -2. How many oxygens do I have? I have 4 times 3, that's 12. 12 times -2 is -24. Oh my goodness. Right, so I know that nitrogen, I have 4 nitrogens. When I'm looking just at nitrate, I'm going to draw this over here. When I'm looking at nitrate, I know that it has to have the charge of -1. Each one of those oxygens is a -2. -2 times 3 is -6. To keep a -1 charge overall, the nitrogen has to be a +5. -2 times 3 is -6. If nitrogen is +5, then the whole thing has a charge of -1. So my nitrogen here is a +5. I have 4 of them. 5 times 4 is a +20. So I have -24 and +20. This iron now needs to be a +4 in order to balance out the 20 and the -24. So the oxidation state of iron is +4. The oxidation state of nitrogen is +5. The oxidation state of oxygen is -2. We're going to call this guy iron 4 nitrate. H because it's a polyatomic ion. Good. So now we're going to look at some guys that are not transition metal compounds. We're still going to find their oxidation states. So I've got sodium phosphate here, sodium phosphate. I'm going to start with that oxygen. I like to start all the way on the right. Oxygen's a -2. -2 times 4 is -8. I'm going to go all the way over to the left now. Sodium is almost always a +1. +1 times 3 is a +3. So I have +3 and -8. In order to get that to balance out, my phosphorus has to be +5. So sodium's oxidation state, is +1. Phosphorus is a +5, and oxygen is a -2. Good. Let's do O3. That's just oxygen, so it's going to be 0. It is just oxygen. There's nothing combined with it. These oxygen atoms are sharing electrons. The oxidation state of oxygen in ozone is 0. Iodine chloride. You're like, they're both halogens. They should both be -1, except because chlorine is more to the right in this formula. It's more electronegative. We're going to give it the -1 charge, which leaves iodine to be a +1 charge. All right, this last guy, H2C2O4. Oxygen all the way to the right is a -2. -2 times 4 is a -8. So we have a total -8 charge coming from those oxygens. Let's flip all the way back over to the left. Hydrogen is going to be a +1. +1 times 2 is +2. So I have +2 and -8. To get to 0, I need a +6. I have 2 carbons that need to add up to a +6, which means that each one of them needs to be +3. So hydrogen's oxidation state is +1. Carbon's is +3. Oxygen is a -2. Good. All right. So let's go ahead and do another equation. Chlorine gas by itself is going to have an oxidation state of 0. Iodine, when it's not with another halogen or oxygen, it's going to be -1. Potassium will be a +1. Potassium chloride, the chloride is now -1. Potassium is a +1. Iodine by itself is a 0. So now I want you to figure out which species was oxidized. Remember that means losing electrons, Who lost electrons? Well, it looks like iodine did, because iodine went from a -1 up to a 0. It used to have an extra electron, and now it doesn't. So iodine was oxidized. Iodine was oxidized. What we're going to do now is build a half reaction. A half reaction for iodine was oxidized. So iodine was still oxidized. I'm going to put those charges back up there super quick. Iodine went from a -1 to a 0. I'm going to write a half reaction showing just that. So I only care about iodine and its electrons. So I used to have 2 iodides actually. I had 2 iodides, that negatively charged ion. It gave away 2 electrons, and what was left over was I2. That was neutral with a 0 charge. Good? So this would be the oxidation half reaction. The half reaction showing just the half of the reaction that is oxidation. This is our oxidation half reaction. Let's do the same thing for reduction. So I've got those oxidation states back up here. Good. We know that iodine was oxidized. It lost electrons. Who was reduced? Who gained electrons? Well, chlorine went from a 0 to a -1. Chlorine's charge went down to -1 because chlorine gained electrons. It got some more, and so chlorine was reduced. I'm going to write a half reaction showing just chlorine being reduced. So we're going to start with just the chlorine. We're going to add those 2 electrons that iodine gave away. We're adding those to chlorine, and we're going to make 2 particles of that anion chloride. This is our half reaction, just half of the reaction showing reduction, our reduction half reaction. And my friends, we did it. We defined oxidation and reduction. We figured out what oxidizing agents and reducing agents are. Oxidizing agents are reduced. Reducing agents are oxidized. We practiced a lot of oxidation states, and we wrote a couple half reactions. Good work.